Hello, so in this video we're going to be talking about this thing called complex integration. But I want to introduce, or at least kind of define the ideas behind real integration first, in order to really understand what's going on with complex case. Okay, so with a real function, let's say we have a real function, okay, so I'm just going to draw it out. We've got x along this axis and y along this axis, okay, and we've got some function going on like this, all right, and this function is just going to be called y, is going to be equal to some function of x, so it could be, literally any function of x you like, it could be polynomial, cubic, quartic, whatever, okay, it's any function you like, and basically what we want to do is we want to try and define the area underneath this curve. Well, how are we going to do it? We're going to start at some point. That's going to be A, okay? And then we're literally going to walk or travel along this curve, okay? Summing areas as we go. So we're going to be taking the area underneath the curve as we go. And we're going to finish at some point B. So this should be a straight line. So we're going to finish at another point over here, which is B. So basically, from A to B, this is the area which we want to add up. We're going to literally walk along this, and then basically each step that we take, we're going to be taking the area of the step that we've just travelled. Okay, so if we take the area of the step we just travelled, so let's say we go from here to here, right, and we take that area in there. Maybe if we just get rid of that. There we go. So we've taken that step there, we take the area of that, okay, then we take that step there, and we're going to take the area of that, okay, and then we take another step, and we're going to take the area of that, yeah, and so on and so on and so on until we take the area of the whole thing. Okay, so we're going to carry on like that, and we're going to take the area of the whole thing just by kind of summing the areas we go. Well, what is the value? How are we going to work out the value of each of these areas? Well, that's quite easy actually. We're just going to consider it as a rectangle. Okay, so maybe that's not the best rectangle in the world. That's a little bit better. There we go. So this is basically the rectangle. Okay, this is basically each rectangle. Well, what is this value along the bottom here? What's the what do you call it? Width, I suppose. Width of this rectangle. Well, it's just going to be the step size. Okay, and the step size is going to be defined by the change in x. Yeah, because each step that we're taking it in a kind of a horizontal direction. So it's going to be defined by the change in x. Okay, the change in x, which remember we just write, it comes from physics. We write change by the value delta, the letter delta. Okay, what's the length? What's the height of this rectangle? Well, the height is going to be defined because we're taking it from the x-axis. It's just going to be the height of whatever the value is at the function at that point. Yeah. So the value of the function at that point is just going to be f of x. Yeah. You happy that the height of that function is just going to be the height the height of the rectangle is just going to be whatever, because we're taking it to the function itself, it's just going to be whatever the value of the function is at that point. So we're going to say if it's over here, this is f of x. Yeah, this is f of x, this is 0. So whatever that height is just going to be f of x. Okay, so that's kind of what's going on here. So basically what we're going to be doing is taking, this is the area. So how do we work out the area? It's just going to be length times width, effectively, or height times width. So it's going to be f of x times our change in x. Okay, and basically this is just one rectangle. We're going to basically be going from A to B, so from x equals A to x equals B, and we're going to be summing. We're going to be adding all these areas as we go along. So we're going to add that area, that area, that area, that area. All the areas are going to add together, and we're going from A to B. Okay, so this is basically the kind of the idea. But we've got this function, and it's going to be a curve. Okay, and we basically considered it just as a rectangle. The area is just a rectangle. Well, if you notice, if you consider it as a rectangle, so I've blown this up now. If you just consider it as a rectangle, just move that up. If we just consider it as a rectangle, we're going to miss some. Look, we've missed all that bit in there. Yeah, so we're just going to basically approximate it. So it provides a good approximation, but it's not great. It's not an absolute definite integral. So basically what we're going to have to do is, to get a better approximation of this function, we're going to have to consider a smaller and smaller value, or smaller and smaller width, aren't we? Because if you're happy that a curve is just a series of straight lines, in the limit it's just a series of straight lines. Okay, maybe if I make that a little bit bigger. Okay, that's just a series of straight lines. So if I just consider the area of one of those straight lines, eventually it's just going to become horizontal. Okay, and we're just going to end up basically with our rectangle. We could just use our formula for a rectangle. So basically we can consider the area as a rectangle if we take smaller and smaller steps. So the idea is that we want to take a step size which is so close to 0, but it's not actually 0. So it's, in other words, it's really, really close to 0, but it's kind of, if we made it any smaller, it would be 0, so there'd be nothing there. So it's kind of the smallest step size that we can take. And we call that idea a limit. Yeah? Because what we're basically doing is we're considering a step size, which basically approaches 0, and it gets so close to 0, but it's not actually 0. Okay? So in order to do that, we're going to kind of show that with our notation. Remember before we had the sum from a to b of f of x times our change in x. Okay, well now what we're going to be doing is taking the change in x is going to be so small that it's so nearly 0, and we're going to show that it's still going to be delta, but we're going to show it by dx. Okay, d basically is still delta, but instead of it being, big delta, big capital delta is, if you like, a big change. Capital delta is a big change. Okay, little delta is a kind of a small change, but we're considering a tiny change that's so close to 0. So we just want to show that idea by writing just an ordinary d. Okay, so that's just what's going on. It just means change. Okay, so this is f of x times dx, and also we're going to show that with the sum as well, because we're summing basically areas that are so small, that are so close to 0. So we're summing s for sum. So we just show that by an elongated s. Okay, so an elongated s, and we're still going over the same limit from a to b. Okay, so this is basically how we define an integral in real numbers. This is what is literally going on when we integrate something. It's finding the area underneath the function, but we're considering such a small area. So hopefully you followed that. Okay, but consider it that in a real case, it's only one path, because y is defined as some function. It's only one path. Yeah? It's only one path we can travel on. We can only travel along the function. So now we want to basically consider the case in the complex case. So that was the real case. Now I want to basically consider the complex case. Okay, so now with the complex case, we've got, let me just draw in a complex plane. Okay, so this is the real plane, and this is the imaginary plane. Well, basically, say now if we want to find the integral between two complex numbers. So we've got a complex number here. Let's call it, what are we going to call it? We've got a complex number here from, well, let's just consider this. So we've got this complex number here, which is Z1, and this complex number is Z2. Well, in actual fact, there are an infinite number of possibilities of routes that we can take. So we can either go directly from Z1 to Z2 in a straight line, but we can also take, a really weird path. We can take an infinite number of paths. If you like, we can keep going all the way to the other side of the universe and come back to Z2 if we want. Okay, basically the idea is there's an infinite number of paths to get from Z1 to Z2. So what we basically need to do is we need to sort of somehow define a curve. So we need to parameterize a curve. We need to make up a curve that kind of defines the distance between Z1 and Z2. Okay, so in order to do that, let's say that this is, let me just rewrite this out again. So let's say that this is A. Okay, this is A. And this is B now. These are just 2 points in the complex plane this time. It's not the real plane, it's the complex plane. This is real, and this is imaginary. Okay. Then what I'm going to do is I'm going to parameterize my a curve in a complex plane. So I'm going to parameterize a curve. I'm basically just going to draw a curve in, and I'm going to parameterize it as z of t, so complex numbers over time, is going to be given by a real component over time plus an imaginary component over time. Yeah. So that's basically what's going on there. So from A to B, I've basically parameterized it, presuming that t goes from A to B. So this is just parameterizing. It doesn't worry about too much of that. So basically go from A to B, I need to kind of come up with a curve. I need to parameterize a curve, make up a curve that allows me to go from A to B, if you like. It's going from Z1 to Z2. So I'm just showing that we can go from Z1 to Z2. Okay, so the way to do it is basically this curve is going to be made up of a series of complex numbers because it's in the complex plane. So each point on this curve will correspond to a complex number. So it corresponds to, say, like Z1 is obviously the first one. Then we go Z1, so Z. Maybe this isn't the best notation, but Z. What is it? Is going to be Z of. This is. Let me just rewrite this. This is basically time naught. At time naught, where am I going to be? Well, I'm going to be at A. So I'm going to be at Z of t naught. Z at t naught, I'm going to be at A. Okay. And then at Z of t2, I'm going to be at. Z at t n, I'm going to be at B. Okay. And then basically I can subdivide this interval. So basically this will be at this point here will be at Z of t1. Z of t1. This point here will be at Z of t2. okay, z of t2, z of t3, z of t4, etc., 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 all the way up to z of tn. So basically what I've now done is subdivide my interval into z of some time. Okay, well let's stick with the notation that when I'm at A, I'm considering Z1, okay? And then when I'm at B, instead of calling it Z2, because otherwise my notation will become a bit sticky, I'm just going to call it Zn. So basically go from Z1 to Zn, okay? Well, what I can do is I can move from Z1, Z2, Z3, Z4, okay, right the way up to Zn, minus 1 to Zn. Okay, so basically these are the complex numbers which I'm moving through. I'm literally moving along this curve. This is Z1, Z2, Z3, Z4, Z5, Z6, Z7, all the way up to Zn. Okay, so Z of T0, I will be at A, and Z of Tn, so if you like, this is Z1, okay, I'll be at A, but then at Z of Tn, so if you like Zn, I'm going to be at B. So in other words, my subscript just corresponds to kind of what time period I'm at. Maybe I should call that Z0. Yeah, just corresponds to that. So Z of T0, I'm just going to rewrite Z0, and Z of Tn, I'm just going to write Zn. So Z of Z0, I'm going to be at the start of my interval, and Zn, I'm at the end of my interval. Hopefully I made that a little bit clear. Okay, so the idea is, just remember, go back to our real case, where I'm basically splitting this curve up into lots of different strips. Okay, so in other words, I want to form a sum. And my sum is going to go from r equals 0 to r equals n. Okay, so I'm basically going from z of 0 right the way through to zn of my function, which is now defined by a complex number. So my function, which is this part, so if you like, it's the imaginary part of my complex number. Okay, the imaginary part of my complex number, I'm just going to write that as psi of r. Okay, so that all that just corresponds to is the imaginary part of my complex number at each point in time. Okay, and then basically what I'm going to do is find the I'm going to find the change which I've moved through. Okay, I'm going to find the change which I've moved through. And the change which I've moved through, just like I did before, is kind of like the change in my x. So this is, if you like, this is the height of my rectangle. Okay, height of my rectangle is, and I'm using this kind of different notation just purely because it's now complex. Okay, it's exactly the same idea. This is the height of my rectangle, and that's going to be defined by the function. Okay, my function, which of course is going to be some imaginary part of my number, and then this distance here. Well, say if this was at ZR, so just some general point. Okay, so say if I'm over here, I'll be at ZR. It could be Z1, Z2, Z3, whatever. I'm at ZR. Then basically, what have I moved to? Well, I've moved from ZR minus 1 to ZR. Okay, I've moved through that distance there. It's the same thing. I'm just trying to find the area underneath that thing there. Okay. I've moved from ZR minus 1 to ZR. So are you happy that the change which I've moved through, is ZR minus ZR minus 1? Yeah? I've moved from ZR minus 1 to ZR. So that change there is just going to be ZR minus 1. Okay? And I'm taking the sum. And then it's exactly the same idea to the real case. It's exactly the same idea to the real case, the thing which I defined before. Except now I'm having to use a different notation where this was x. Okay, I can't no longer use x, and I can no longer use delta x because I'm not. I can't use it because I'm now using a complex number. Okay, and each point, if you like, corresponds to a complex number, and a complex number is going to be defined by x plus iy in general. So basically, what I've done is I'm wanting to move from this point here to this point here. So what I've had to do is kind of define a curve, and I've defined a curve by taking a parameterization of it. Okay, and then basically what I'm having to consider is each case. I'm considering each case, each point along this line will correspond to a complex number, fairly obviously. And that complex number will correspond to a real part, which is f of zeta, times the imaginary part, the change in the real part, which is this part. So this is an imaginary part, this is the change in the real part. And it's basically, I'm just considering a rectangle. So hopefully I've made that fairly clear. Okay. Well, basically, as I take the limit, so in other words, as this distance tends to 0, and basically I take more and more complex numbers, so I'm considering more and more complex numbers. So in other words, I'm taking ZR minus ZR minus 1, as that tends to 0, so smaller and smaller distance, smaller and smaller horizontal distance, yeah, this is Z1, this is ZR minus 1, and basically as I'm taking more and more complex numbers, so n tends to infinity, right, so as n tends to infinity, I'm going to basically end up with the thing I want. So it's the same kind of idea as before. I'm going from over a closed curve now, going over a closed curve of f of z. Sorry, I'll come on to why it's closed in a minute. Come on, get rid of you. So I'm going to go over my curve C of f of my complex notation. Remember before, my complex notation was just using zeta. Okay, it's just kind of like a general complex imaginary part. But now I'm saying, well, okay, it's going to be an actual real number. Okay, times dz. It's kind of, don't get too bogged down on the notation. If you can understand the real case, then hopefully you can see how it applies to the complex case, except instead of just using real points, I'm now having to define it in terms of imaginary and real parts, because it's a complex number. Okay, it's kind of a very similar idea. If you want, you can just ignore everything I did before this point, just from the real case, ignore everything I did up to this point, and hopefully you can see just by similar ideas that that's very much still what's going on, that, you know, the same idea is what's going on, but I just have to define it slightly differently because it's complex. Okay, it's the same thing. Also we have to say that the curve C, we have to define the curve C, because remember, there's an infinite number of ways of getting from Z1 to Z2. So if you like, this is A and this is B. Yeah, it's an infinite number of ways of getting between these two complex numbers. So I basically have to say this only works over a closed curve. Closed curve. So in other words, a closed curve means that you start and finish at the same point. So you travel along a curve, okay? So you go from, say, Z1 to Z2. Okay, so you travel along a curve to get from there to there. But the idea is that also you can travel along the same curve to get the way back. So this is, if you like, the whole curve is closed. You start and finish at the same point. If you carry on a full cycle of that curve, you start and finish at the same point. So in order to show it's closed, we just write a little closed circle there. Okay, so that's the only idea which kind of you need to understand. So this is very much motivation for trying to show you where this comes from, where this idea comes from. Like I say, if you can understand the real part, great, because this part this complex case just carries on.